यार କାଲି ଦଉଥିଲା ଆଜି କାଇଁ ଗଲେ?
Yeah, good morning all.
Good morning, sir.
Yeah. All are fine?
Yeah, sir.
Right. Let's start the class.
Why not, sir?
Okay. Right. Some issue in the secondary class, a technical issue. That is, it takes to clear. Times it takes time to clear. Okay. Due to that reason, I'm going to start this lesson very late. Okay. Please understand the problem. Yeah. Yesterday we stopped at Hookel rule, I think. Yes.
Yes, sir.
Okay. Right. Let's start the Hookel rule. Yeah. For explaining aromaticity, we have two rules are there. Actually, two rules we can call it as also two theories. One is Hookel theory, and another one is Mobius theory. Hookel theory and Mobius theory. What is Hookel theory and what is Mobius theory? First, aromatics explained by. My voice is audible here?
Your voice is breaking, sir.
My voice is breaking.
Yes,
Now
sir.
it is okay? Now it is okay?
No,
Yes,
sir.
sir.
It's breaking.
It is okay, sir.
Okay. For the bandwidth, I'm closing my video. Right? I think it is very well. Yeah, I'm closing my video. Right? Now it is audible clear.
Yes, sir.
Right. Aromaticity is explained by two theories. One is Hookel theory. And the second one is Mobius theory. First, you coming to Hookel theory. Coming to Hookel theory. Yeah, please stop the animation. It creates the confusion. Okay. Please delete it. Who made this animation? Please delete it. Don't use this symbol, animation symbol. Don't use this. Right. Hookel theory. What Hookel theory tells? What is the basis for the Hookel theory? In both the theories, basis is molecular orbital theory. Basis is molecular orbital theory. Yeah. According to Hookel theory, planar monocyclic polyene with 4n5 plus 2 electrons are aromatic. Are aromatic. Are aromatic. Right? Why these are aromatic? And again, is also stated that the same planar monocycle poly with only 4 are anti-aromatic. Are anti-aromatic. For example, for this, benzene is the example. Everybody knows the R double bonds and the 3 double bonds are there. Therefore, 6 pi are there. 6 pi electron to 4 is very n is equal to 1. Similarly, for this we can take cyclobutadiene. Cyclobutadiene. It is the 4th electron. It is having n electrons. N is equal to 1. Where n is equal to 1. Now, according to MOT, what is MOT? Molecular. Yes, according to molecular orbitality, orbitals undergoes linear overlapping, linear addition, are combined together. They produce the equal molecular orbitals. For example, in the case of benzene, is benzene. In the previous class also, I have shown the unhybridized orbital. Those are the atomic orbitals. The unhybridized p orbital, which are perpendicular to the plane originally. The geometry is perpendicular to the plane. 6 p orbitals are undergoing linear combination. Linear combination of orbitals. They produces equal number of this is the non-bonding molecular orbital energy level. Now the 6 atomic orbitals are combined together. In that 6 atomic orbitals, 3 atomic orbitals, 3 molecular orbitals are generated, called as bond molecular orbital, which is due to the addition of the functions. Addition of the wave function leads to the formation of these molecular orbitals, which is having lower energy than the non-bonding energy level, or we can also call as we can also compare with the energy of unhybridized p orbital. Unhybridized p orbital. Therefore, we can write it like this. 1, 2, and 3. I'm just showing energy levels, but it is simply 2, 3. These 3 are the bonding molecular orbitals, right? And Three of them are anti-bonding orbitals. Right? Yeah. This approach is explained by the molecular orbital, but some extension is proposed by the Huckel. These molecular orbitals are arranged in different manner by the Huckel team. Suppose these are the molecular orbitals of the benzene, right? Where how many number of molecular orbitals are there? 6 molecular orbitals are there. Therefore, the number of molecular orbitals, if it is n, if it is n, these molecular orbitals are arranged like this. Suppose the number of molecular orbitals are like this. This is the non-bonding energy level. And if the molecular orbitals are
Sir, voice is not clear.
n is equal to even, for example, n is equal to 6. N is equal to 6. In that, three of them are molecular orbitals. Three of them are anti-molecular orbitals. Right. When we comparing the energies, 3 bonding molecular orbitals are having lower energy than the 3 anti-bonding molecular orbitals. Again, these 3 bonding molecular orbitals, one is having least energy and 2 are having the same energy. Look at here. The bonding molecular orbitals of 3 bonding molecular orbitals are arranged like this. One, this is the psi 1, lowest energy bonding molecular orbital it is. And remaining 2 bonding molecular orbitals are equally energized. This is called doubly degenerate molecular bonding molecule. It is shown with the right. The same way, anti-bonding molecular orbitals. Anti-bonding molecular orbitals. The 2 are the doubly degenerated anti-bonding molecular, and one of them is having highest energy bonding orbital. Bonding molecular orbital. Right. Now, when you same number, right? Right. Now, in this all, look at here. 6 unhybridized p orbitals are there. The 6 unhybridized p orbitals are having 6 pi electrons. 6 The 6 pi electrons are filled into the molecular orbital by based on the Aufbau principle, Paulus exclusion principle, and Kunz rule. Based on that, that is, the electrons are filled into the molecular orbital by increasing in such a way that increasing order of the energy of the orbitals. First, least energy orbitals are filled. Now, the first 2 electrons are filled into the least energy bonding molecular orbital. Least energy bonding molecular orbital. Right? First 2 electrons are filled into this. Again, the 2 doubly degenerated bonding molecular orbitals are there. The remaining 4 electrons filled into first 2 electrons equal. The remaining electrons are also shared. All the 6 electrons are filled into bonding molecular orbitals. Now, this is known as closed configuration. Shell electronic configuration. Electronic configuration. Based on this, I'm showing you in general molecular orbitals are arranged based on the Hückel rule and how the electrons are filled. Look at here. Can I shuffle to above? Yeah, I'm moving the slide to above, right? Please remove these annotations. Those who are making this annotation. Please remove this. Annotate, please remove this. Those who are making this. Now, if aromatic system with even number of molecular orbitals. This is the non-bonding energy levels, nothing but the energy of level is equal to energy of the p orbital. That is non-bonding level. NB non-bonding energy. Or it is also called non-bonding molecular orbital level. Right. Suppose here the n is equal to even. In that n by 2 bonding molecular orbitals, n by 2 number of anti-bonding molecular orbitals, right? 0. Right, just a minute. Right. Leave it. Okay, now don't worry. 0 number of non-bonding molecules. 0 number of non-bonding molecules. Suppose if in the aromatic system it contains any number of molecular orbitals, those that n is equal to even number, where n by 2 number of bonding molecular orbitals are there, n by 2 number of anti-bonding molecular orbitals are there, and 0 number of non-bonding molecular orbitals are there. In which, right, where n by 2 number bonding molecular orbital is least energy bonding molecular orbital. The remaining are n by 2 minus number of molecular orbital, bonding molecular orbitals are doubly degenerated molecular orbitals. Doubly degenerated bonding molecular orbitals. Here also it is where one anti-bonding molecular orbital is highest energy, and the remaining n by 2 minus 1 of molecular orbital anti-bonding molecular. Look at here. I am arranging like this. One is the least energy bonding molecular orbital. This one, right? The remaining n by 2 minus 1 are doubly degenerated. Like this. And so on. Highest energy orbital, anti-bonding molecular orbital. This is the least bonding molecular orbital. Suppose if we take this one, and this is the degenerated bonding molecular orbital, right? And side At the same time, one of them is the highest energy anti-molecular orbital. It is taken psi and doubly degenerated orbital. Psi minus psi minus 2 psi n minus. This is the arrangement of molecular orbitals of aromatic system. In previous one, look at here. Molecular orbital theory is proposed like this. Atomic orbitals are undergo the linear combination that produces the molecular orbital. The molecular orbitals are arranged like this. But Huckel is modified these molecular orbital arrangement like this. Based on this arrangement, he filled the electrons of that aromatic system. If the filled electrons are occupied the orbitals in such a way that it is showing closed electronic configuration, that is known as aromatic. If it is closed electronic configuration, that is known as aromatic.
Sir, why there is doubly degenerate state more than
what is the degenerated state you are asking?
No. My question is that why there is only two, means two orbitals are there.
Yeah,
two.
Yeah, tell me.
More than two orbitals is possible or not?
More than two orbitals may not arrange it in the same wave function, same wave level, wave energy level, right? It is the maximum possibility to orient in the same wave function energy level is the maximum is two orbitals as per the quantum mechanical rules. Based on that, Huckel is arranged these two orbitals in the same energy level. If you are going there, it is happen in the case of metal complexes. Only d orbitals are having the doubly degenerated and triply degenerated.
Yes, sir.
Yes, that is the d orbital. But here we are all dealing with the p orbitals. In the case of p orbitals wave function, the maximum possibility to having the same energy by the two orbitals only. That is the reason. Yes, that is involving the more complex nature of the quantum mechanical calculation. Those who are not dealing here, okay, that is purely explained in the quantum mechanics.
Sir, actually, what is degenerated orbital?
Yes?
What is degenerated orbital?
Degenerated orbitals are having the same energy.
Sir, and the doubly degenerated means?
Doubly degenerated. Doubly degenerated means these two are doubly degenerated. Two orbitals are degenerated. That is called, I'm indicating it doubly degenerated. Double degenerated.
Okay, sir. Okay.
Bonding molecular orbital. You can also simply call it as degenerate molecular instead of you are showing degenerated bonding molecular orbital. Both combined together, you can call it.
Sir, molecular orbital ni doubly degenerated, triply degenerated, differentiation. Sir, sir.
Degeneracy means having the same energy.
Okay, sir. Okay,
having the same energy. Here, the two orbitals are having the same energy. Due to that reason, I am calling it as doubly degenerate.
Ade sir, doubly degenerated, triply degenerated and untadi sir. Adala differentiate chestam sir.
Yes, this is a doubly degenerate. Suppose if you take the d orbitals, I have already explained in the splitting of d orbitals of the metal complexes, tetrahedral or tetrahedral, right? If you are providing some energy, they are split into two types of orbitals. One is with this is called T2G, triply degenerated. Called EZ, doubly degenerated. Okay, here this 5 degenerated. These degenerated orbitals are undergoing splitting whenever we are providing energy in the form of heat or that will be, or it is in the form of electrical or magnetic field. Electrical or magnetic field. These are splitting into two types of orbitals. One is the triply degenerated orbital and doubly degenerated orbital. Here, this is easy indicating only spectroscopic symbols. These are the spectroscopic symbols. Spectroscopic symbols are calculated by the electronic configuration of molecular orbitals, not the atomic orbitals. Electronic configuration symbols are there. Those are called spectroscopic symbols. Based on the spectroscopic symbols, we are labeling with the T2G easy. Right? Here, these three orbitals are triply degenerated. These three orbitals are having the same energy. These are called as doubly degenerated. These two orbitals are having the same energy. Clear? Clear?
Yes, sir.
Yes, sir.
Yes. Right. These are already dealt in inorganic chemistry. That's why I'm not introducing these two directly. I'm using those words. Right. Now look at here. This is about the aromatic system with even number of molecular orbitals. Suppose if you consider where n is equal to odd number, when n is equal to odd number. First, I take the example that is the cyclobutadiene. It is having and like this for clearly show unhybridized p orbital. Right. These are the four unhybridized p orbitals are undergoing LC linear combination of atomic orbitals. It gives four molecular orbitals. As per the MOT, these orbitals, two of them are molecular and two of them are antibonding. Two of them are antibonding molecular orbitals. Now, this is the least energy. Suppose and right. Right. This is about the molecular orbital. But to kill rule, these are arranged like this. This is the non-bonding energy level. One of them in the bonding molecular orbitals is the least energy bonding molecular orbital. Least molecular orbital that is shown with the psi 1. One of them with the highest energy, that is bonding molecular orbital. The remaining two are, I'm showing it. Right. Look at it. These are the non-bonding orbitals. Now, how many electrons are there? 4 p orbital. 4 pi electrons. Electrons are filled. First two electrons psi 1. So this is 4. Right. Now the remaining two electrons equally shared because two of them are having the same energy. Now look at here. These two are having unpaired electrons in the orbitals. These two electrons are unpaired electrons. Now this is known as not closed shell electronic closed, not a closed shell electronic configuration. Right. Not a closed shell electronic configuration. Now this is called as aromatic. This is called as anti-aromatic. Yes. This is the one way. This is the one way. Another way, we can also show the same system in the same configurations. Okay. Huckel is proposed this model, but later it is modified. Look at here. One of the orbital is least and this I1 is this, right? And even number. This is also even number. Why we are using this one, right? Just a minute. Okay. This is the only configuration, but this is restricted to only 5 electrons. 4 electrons. But it will be altered when the number of electrons are increased. Here I am using odd number, but I am taking the even number. Sorry. Okay. Don't worry. I am using here another example. It is also taking for the same example, but n is equal to even number, right? Now here it is anti-aromatic. Not a closed electronic configuration, it is anti-aromatic. Now take n is equal to r. N is equal to r. For example, I am considering cyclopentadienyl anion. Cyclopentadienyl anion. The cyclopentadienyl anion. It is the actually sp3 carbon. The remaining are sp2. But only whenever we are showing the orbital structure, it is the monocyclic. This is the unhybridized p orbital at one center and second, third carbon, fourth carbon, fifth carbon. Now we do formation of molecular orbital. In the 5 molecular orbitals, 3 bonding molecular orbital and 2 are the anti-bonding molecular orbital. Anti-bonding molecular orbital. How it is? The arrangement is like one of them is least orbital, and the remaining bonding molecular orbitals are equally related to bonding molecular orbital energy level and anti-bonding molecular orbital energy. This is 2, 4, and 7. The number of electrons when you coming to here, number of electrons. Here the one carbon is having 2 electrons. The remaining 4 carbon centers, one electron. That means here one pair is there, negative charge is there. Here the 2 electrons are there. 2 electrons and 1 electron, 1 electron, 1 electron. Total 6 pi electrons. Now these 6 pi electrons are filled first lower energy are 2 electrons and 1 electron here and 1 electron, and the 2 electrons are remain and 1 electron is 1 electron. Total 6 pi electrons. It is also showing.
Sir, excuse me, sir.
Yeah.
Sir. మనం తీసుకుంది హార్డ్ గా సార్ n ఈక్వల్ మీరు మళ్ళీ ఈవెన్ తీసుకున్నారు సార్ యాక్చువల్లీ
No, here the
Cycle
number of
అంటే daily
electrons, not the number of electrons are odd. Here I am considering n is equal to odd. That is the number of carbons or number of molecular orbitals are odd number. Please different. That is the reason previous also I have given the same mistake. Right. I am taking here is the even number of molecular orbitals and even number of electrons. Now I am taking here odd number of molecular orbitals. That 5 unhybridized p orbitals are undergoing LCAO. That leads to formation of 5 molecular orbitals. These 5 molecular orbitals are 3 of them are bonding molecular orbitals and 2 of them are the anti-bonding molecular orbitals. Here n is equal to odd number. This odd number indicates the molecular orbitals, not the electrons here. Molecular orbital, where n is equal to number of molecular orbitals. Right. Now this is also having closed shell electronic configuration. Therefore, it is aromatic. Closed shell electronic configuration shown by the closed shell electronic configuration. Therefore, it is aromatic. Now it is following the 4n+2 rule. But in this case, it is not showing any closed shell electronic configuration because there is a vacancy is there in the Psi2 and Psi3 off-filled electronic configuration. This in the 2 orbitals. Therefore, it is anti-aromatic. Now, based on the Huckel rule, by combining with the molecular orbitals, Huckel theory plus molecular orbital theory, the molecular orbital electronic configuration is shell electronic configuration. That is not a electronic configuration, or you can call it unpaired electrons. That is anti-aromatic. Anti-aromatic. Okay, that is the explanation for the, that is also called as rationalization of Huckel theory. Rationalization of Huckel theory. Molecular orbital theory is the basis for Huckel theory. In this, according to the molecular orbital theory, by linear combination of atomic orbitals, Huckel arrived at the molecular orbitals of the pi system. These molecular orbitals may be bonding or anti-bonding, lower energy and higher energy in comparison with the pi atomic orbital molecular orbital. In monocyclic conjugated polyenes with even number of atomic orbitals, there is a lowest energy bonding molecular orbital and a highest energy bonding molecular orbital. All the other molecular orbitals are doubly degenerate and are arranged symmetrically about the non-bonding energy level as shown here, like this. Similarly, general pattern of molecular orbitals in even-membered monocyclic conjugated polyene is shown like this, right? It can be shown that the available number of pi electrons can be accommodated by following Aufbau rule or Aufbau principle, Ohm's rule, and Pauli's exclusion principle. to give the, if it is giving the closed shell electronic configuration, pi electronic configuration, we can also call it as pi electronic configuration. Closed shell pi electronic configuration, that is completely filled bonding molecular orbitals only. When the system contains 4n plus 2 pi electrons, that system is named as aromatic system. Example, you can take benzene, cyclopentadienyl anion, and cyclopropylenium cation, and several molecules are there. In the same way, in a monocyclic conjugated systems, usually maybe ionic, with odd number of pi atomic orbitals, there is a least energy bonding molecular orbitals. I have not given the in general electronic configuration for the where n is equal to odd number. Look at here. If n is equal to odd is molecular orbital. In such case, where one molecular orbital is low energy bonding molecular orbital. One orbital is lower energy bonding molecular orbital. The remaining molecular orbital, that is n-1, are the remaining bonding orbitals. n-1, 2 are the anti-bonding molecular orbitals. This is the way when odd number of molecular orbitals are present in a aromatic system. Now arrange like this. Suppose after deduction of all these things, is there any molecular orbitals are remain? Those are oriented on the non-bonding energy level. Now, one is the one molecular orbital, the lower energy, least energy bonding molecular orbital. This is the least energy molecular orbital. Right? Now, here n-1, where n is equal to odd, suppose this is the n is equal to 5, 5 minus 1, how many it remains? 4. That is 4. That is 2 are bonding molecular orbitals, are the anti-bonding molecular orbitals. Those two of them are doubly degenerated. It is the site. It is the the bonding molecular orbitals as a pair doubly degenerated orbital. Right. In this, there is no highest energy orbital, but you can arrange n psi minus 1, n 2, n minus. When arrangement of molecular orbitals of the pi system or aromatic monocyclic conjugated polyene system with odd number of molecular orbitals. Right. Based on that, we are filled the electrons like this. If you take this cyclopentadienyl anion, the 6 electrons are filled in. First, you are arranged the molecular orbital like this, based on the same rules. These rules were arranged like this, and fill the electrons based on the 3 rules. That is the Kunz rule, Pauli exclusion principle, Aufbau principle. Accordingly, those electrons are filled. If it is showing closed electronic configuration and following Hooke's rule, that is, it contains the 4 and 5 electrons, that is aromatic. Even though sometimes it may happen, still there is no example for that. But in some cases, it may be happen the compound with 4n electrons, but it shows 4 and 5 electrons, but it shows closed electronic configuration, that is not aromatic. That is the exception or limitation for the Hooke's rule. Right? But here, this system is, even though it is the odd number of molecular orbitals are there, but it is sharing 6 pi electrons. The 6 pi electrons are showing the closed shell electronic configuration. It is aromatic. it is aromatic. Okay, this is the general electronic arrangement of molecular orbitals for the system with the odd number of molecular orbitals. We have several examples are there in your book. You can practice it, right? This is called rationalization of Huckel theory. The Huckel statement is simple. What is that? Planar, monocyclic, conjugated polyene with 4n plus 2 pi electrons is aromatic. That is a statement. The rationalization or postulates, we can call it as a rationalization or postulates. That indicates the theory of Huckel rule, how it is adapted for the aromatic system. Okay. Now this is about the Huckel rule and the statements of Huckel rules and postulates of or rationalization of Huckel rule. Now some exceptions are there. Exception for the Huckel rule. Exceptions are limitation. You can call it as anything. Exceptions. The first one, right? Huckel's rule was developed in 1930s. It is long back. Many years later, that means during this time, so much work is going on the same aromatic system. Many scientists are identified several exemptions, several limitations of that rule. And whatever the Huckel proposed, some values, some statistics, those are not matched in the experimental condition. Actually, Huckel proposed the values based on his theory. Those values are only theoretical values. Those theoretical values are not on par with the experimental resulted values. A few exemptions have reported. One, the first one, up to 24 aniline, these are 24 aniline, all anilines obeys up to 24 aniline. All anilines obey Huckel rule.
It means 26 pi electrons, right, sir?
24 aniline, up to 24 aniline.
Okay.
Anilines are obeyed Huckel rule. Up to 24 aniline, whatever it may be, even number of molecular orbitals or even odd number of molecular orbitals, it is existing with like a planar, monocyclic, conjugated polyene with
Sir, your voice is not audible.
మీ వాయిస్ వినబడట్లేదు సార్.
Sir, are you there?
Yeah, I am here, no problem. Right.
Okay.
Right. Yeah, up to 24 aniline, all the anilines with 4n pi electrons, it obeys the Huckel rule. That's the condition. Okay, but now which are not obeying? Above, equal, or above? The 26 annulines. That means the C26, H26. It is also C24, H. Above 26 annuline.
Sir, annuline means what?
And higher annulines. Irrespective of 4n, 5 or 5 plus 2 electrons are non-aromatic. Anti-aromatic, not the aromatic. Non-aromatic. What is non-aromatic? What is non-aromatic? Aromatic is the compound which is having the energy when we compared with the same system of acyclic system. Same acyclic conjugated polyene system. Right. Anti-aromatic is the system which is having the higher energy than the acyclic conjugated polyene system. Now, non-aromatic is the system which is having the same energy with the acyclic conjugated polyene system. That is non-aromatic. Now here, whether it is maybe 4n5 system or 4n5 electron system, with the carbon number of carbons are 26 or above, are aromatic. Why are non-aromatic? Why these are non-aromatic? Because these are
Sir, voice is not audible, sir, clearly.
Sir, can't hear you. Meeting over.
Sir, are you there?
Meeting over, sir.
Hello. Hello.
Hello.
am I audible?
Yes, sir.
No, sir.
Yeah, am I audible to you?
No, sir, in between you are not there.
Yeah, actually, electricity problem. Am I audible now?
Now
Yes,
it's
sir.
audible, sir.
Now it is okay?
Yeah.
Yes, sir.
Yeah,
Yes, sir.
I will continue. Right.
Sir, annuline means atomic number or क्या है?
Yeah, you not the atomic number here, the number of carbons. And 24 aniline, we called it as 24 aniline. Yesterday, suppose you take the benzene, 6, right? C4H4, the 4.
Sir, voice is breaking, sir.
Yeah, actually, it is a poor connection. I am taking the internet connection from my phone hotspot. Here, the power is not there. Due to that reason, some lagging is there, network lagging is there. Right? It may take 10
Yes,
to
sir.
15 minutes to recover, right?
Sir, aniline means which atom is have 7 or more carbon atoms. May named as aniline, right?
Not, no need to number of carbons more than 7.
Okay.
Any carbon compound which is having the CN and HN molecular formula is aniline. But the criteria is it should be planar, monocyclic, conjugated polyene.
Okay.
Right? Right?
Okay, sir.
Right. Now, coming to this point, in 1965, Diwar and Gleacher calculate the resonance energy of anilines by using the refined method. Refined method means some spectroscopic method, some chemical reaction methods. Several methods are there, refined methods. Okay, we cannot say not only one method is the refined method. Several refined methods are there. They are used for the calculating the resonance energy. In that, he made the only 3 observations. All anilines having 4n plus 2 electrons up to 22 anilines have positive resonance energy. Again, I am repeating. All anilines having 4n plus 2 electrons up to 22 aniline have positive resonance energy, and therefore all those are aromatic. They study clear that any carbon system, polyene system or pi system that is monocyclic and planar, which contains the 4n plus 2 electrons, and it is a aniline that is showing positive resonance energy. Previously, we calculated the resonance energy for the benzene. What is that? Some 150 or some energy is there. That is the positive energy, not the minus. Right? 120 for the one double bond, 120 one double bond. Right? For 3 double bond, it should be 360 minus is the theoretical value. The experimental. You detected how much it is? Almost 150. Is the 152 is the plus 152. We're not indicated. Kilos of resonance energy. It is the resonance energy. This resonance energy is positive resonance energy. Whenever the molecule is existing with positive resonance energy, that is the aromatic. Okay, it is the negative energy, negative resonance energy. It is existing with negative resonance energy. That is non-aromatic. Right? Non-aromatic. We can also hear some confusion is there. Non-aromatic, sometimes it is having the same energy with the acyclic conjugated polyene. When we comparing the double bond, what we call a hydrogenation reaction takes the evaluation of 120 kilojoules for the benzene. Similarly, some acyclic system is also showing the 120 for the one double bond. 3 double bonds are there, 360. If it is the non-aromatic, it is also showing the 360 kilojoules for more. If it is having 3 double bonds. Then when we deduct it, the resonance energy is 0. When it is showing the 0 resonance energy, that is the non-aromatic. Non-aromatic. It is showing 0 resonance energy, that is non-aromatic. Whenever it is showing negative resonance energy, that is anti-aromatic. Actually, this is the criteria based on the Huckel theory. But these Dewars and Gleichers not at all used the word anti-aromatic. They simply classified the aromatic cyclic conjugated polyene system into two types. One is the aromatic and another one is the non-aromatic. They're not utilizing the word anti-aromatic. Okay. Here also, they proposed that Dewar and Gleicher are proposed that all anilines are having 4-5 electrons up to 24 anilines having negative energy, negative resonance energy, and are non-aromatic. Again, I am repeating, please listen carefully. All anilines having 4-5 electrons up to 24 anilines having negative resonance energy are known as non-aromatic. And next one, all higher anilines, irrespective of 4n or 4n plus 2 electrons, having negative resonance energy, and therefore they are classified under non-aromatic. Dewar and Gleicher's given 3 statements under the limitations of Huckel rule. One statement is all anilines are having 4n plus 2 pi electrons up to 22 anilines have positive resonance energies and are therefore aromatic. And second one, all anilines having 4 pi electrons up to 24 aniline have negative resonance energy and are non-aromatic. All higher anilines, third statement, all higher anilines, irrespective of 4n or 4n plus 2 electrons, are having negative resonance energy and therefore are non-aromatic. Based on the three statements, clearly indicates that what are the limitations of Huckel. Next.
Sir, once repeat, sir. Sir, once repeat.
Yeah, you can repeat the same video in the YouTube. You can rewrite your notes also. Okay.
Oh.
Okay. Next, second limitation. Huckel rule is of limited applicability. Limited applicability. It is that it is only concerned about the monocyclic systems. What is the statement of Huckel rule? Huckel rule is planar monocyclic conjugated polyene with 4 and 5 electrons are aromatic. It is only limited to monocyclic systems. Fused ring systems are not explained by the aromaticity of fused ring system is not explained by the Huckel. Therefore, Huckel rule is of limited applicability. It is concerned only with the monocyclic conjugated system. It provides no clue regarding the aromaticity of polycyclic conjugated systems. Always, Huckel is taking the basis aromaticity of monocyclic, but it is not explained by the aromatic of the fused ring system. Even though these are the phenol, the polycyclic systems. These polycyclic systems is not explained. Okay. Even though having the plus 2 electrons. Okay. The applicable for the cyclic systems. But it is applicable for the because he is not made a single sentence about the fused ring systems of fused ring systems aromaticity. Right? Because we have several compounds. He is not at all mentioned anywhere. There are several polycyclic systems, even though with 4 and 5 electrons, but it is showing aromaticity. For example, these are the limitation. These are limitation of the Huckel here. Right. It is with 16 pi electrons. 16 pi electrons. Suppose you have 4 electrons, where n is equal to 2, n is equal to 3, 12 plus 2, 14 electrons. Or if it is n is equal to 4, 16 plus 8, but it is having 16 electrons. 4 electrons. That is 4 electrons. That is 16. It obeys 5 electrons. That is the Mobius rule. Mobius rule. But it is showing aromatic property. Aromatic property. All the characteristics of features of aromatic compounds are satisfied by this pyrene. This name is pyrene. Pyrene is aromatic. This pyrene aromaticity is not explained by the Huckel. And another one, acetylnaphthalene. Yes, I remember there about the. Yes, this is known as acetylnaphthalene. It is 4 pi electrons. That is 4 into 3 pi electrons. 12 pi electrons. It is also aromatic, but showing aromatic nature is not explained by the Huckel rule. And another one, fluoranthene. Anthene. So the acetylene, it is also aromatic. The aromatic property of these compounds are not explained by the aromatic property of these compounds are not explained by the Huckel rule. Now, next, some of the compounds, there are some polycyclic conjugated system with the 4 and 5 electron system are showing non-aromatic property. Like, look at this is acetylpentylene. Acetylpentylene. This 10 electron system is a 10 pi electron system. Is not the same way pentylene. If it has 5
Sir, your
tell me. Ask me, please.
అంత బ్రేక్ అవుతుంది సార్, ఏం అర్థం కావట్లేదు సార్.
Benzopentylene. Again, first you take the structures. These are the aromatic. Look at here. We are discussing here the limitations of Huckel rule. Right? According to the Huckel rule, any compound which is a planar monocyclic conjugated polyene with 4 and 5 electrons is aromatic. Right? How it is aromatic is explained by the basis of molecular orbital theory. Okay, that is the rationalization of Huckel theory is explained. But when we come into the Huckel theory, the fundamental thing is the compound should be follows the Huckel rule and shows the aromatic property, right? But some compounds are, even though are having 4 and 5 plus 2 electron system, are not showing aromatic property, and some of them are not having the 4 and 5 electron system are showing the aromatic property. That is the limitation. Why these are showing limitations means is not explained by the Huckel rule. That is the limitation. Actually, these two are satisfy the Huckel rule. That's Huckel rule. But not aromatic. These are not aromatic. Not aromatic, these compounds. Why? That is not explained by the Huckel. Okay, there are 3 limitations are there. In the 3 limitations, up to 24 anilines all are obeying the Huckel rule, but above 26 anilines are not obeying the Huckel rule, is not explained by the Huckel. That is the first limitation. And the second limitation, Huckel rule is applicable only for the monocyclic systems, not applicable for the polycyclic systems. He is not mentioned anywhere in his theory. That is the second limitation. And the third limitation, some of the compounds are having 4 and electrons are showing aromatic property, and some of the compounds are having 4 and 5 electron system, 4 and 5 plus 2 electrons are not showing aromaticity. Is not explained by the Huckel. These 3 are the major limitations for the Huckel rule. Did you get?
Okay, sir.
I'm expecting response from you.
Yes, sir.
Okay. Whenever
Yes,
the same question is encountered in the examination, the short answer question may appear in the examination. You need to write these 3 limitations by showing some examples, whatever examples I have given here. You show those 3 examples and explain it. Okay. This is about the limitations of Huckel rule. Now, for explaining aromaticity of so many compounds, there is a rule, or say there is a theory is there that is called Proust-Muslin diagrams. Next one is Proust-Muslin diagrams. What diagrams are showing how these diagrams are helpful for the explaining the aromatics. Right. Proust-Muslin method gives a simple or simplified representation of the Huckel molecular orbitals in all monocyclic fully conjugated systems. Actually, in previous case, we are applying the molecular orbitals for the aromatic system by the help of Huckel rule. Okay, here the Proust-Muslin, these are the 2 scientists, Proust and Muslin. These are picturized the how these doubly degenerated and singly degenerated orbitals are oriented and above and below the non-bonding energy level by drawing some diagrams. Based on the diagram, we can understand that how these molecular orbitals are arranged above and below the non-bonding energy level. Right? Again, I am repeating, Proust-Muslin method gives a simplified representation of the Huckel molecular orbitals in all monocyclic planar conjugated polyene system, including non-benzenoids and benzenoids. What are the benzenoids and non-benzenoids? We will see later after this series. After this topic, we will discuss about the benzenoid and non-benzenoids. In this method, the cyclic conjugated system considered as a regular.
Sir, there is a lot of disturbance.
Please mute all of them. Those who are making noise, please mute. Yeah. Smita, please mute yourself, or otherwise I will mute it. Yeah, I will write the points, major points. I feel you don't hesitate to write. Can I take some time to write? Yeah, okay. Prost-Muslin method is a representation of Huckel molecular orbitals in all monocyclic conjugated including benzenoids and non-benzenoids. Benzenoids, non-benzenoids. According to this system, in this method, the cyclic is considered as sides or M-sided or polygon, where M is equal to number of atoms in the right. The polygon inserted. Look at here. The polygon inserted. Suppose you take the circle. You should insert that polygon in such a way that like this. This is the trigonal system or triangular system. Right? The polygon is inserted into a circle which is divided by vertical and horizontal axis. Vertical and horizontal. Look at here. I'm drawing a vertical axis. This is the vertical axis. This is the horizontal axis. Now this horizontal axis considered as non-inertial. Right. After that, you insert the polygon is inserted into a circle in such a way that one of the carbon considers, one of the carbon coincides with the vertical axis at the bottom. Look at here, I am inserted triangular. Okay. Cyclopropylene molecule. In that, this one of the carbon is touches to the bottom most edge of the circle. That means not only in this case, in any case of the cyclic system, that polygon is inserted in such a way that one of the carbon should be touches to the bottommost point. This is the, when you are drawing the vertical line, the vertical line touches at bottommost circle point is, you need to, the same point is taken as the reference to place the one of the carbon center of the polygon at that place. Therefore, the polygon is inserted into a circle in such a way that one of the carbon coincides with vertical axis at the bottom. It is treated as molecular orbital of polygon having least energy bonding molecular orbital. Suppose in this polygon, this touches this place. This is the carbon. This carbon point is considered as least bonding molecular orbital. That is explained the next point. The polygon is inserted into a circle. Sorry. In such a way coincides with
Sir, in
vertical.
all picture, we should have placed one point in the lower part of
Yeah,
the
I will show
circle.
you all the ring systems. I will show you all the ring systems. So whenever I am showing the diagram, I will tell you why we are inserting that like that, right?
Yes, sir.
Coincides with the vertical axis at the bottom is as molecular orbital of polygon and least energy. This is why we are inserting that in that way, right? In the BMO level, that should have the least energy, right? Next, the other molecular orbitals, suppose after inserting that polygon in a circle, the other molecular orbitals are located wherever the carbons of the polygon touches the circle, and these molecular orbitals will be paired. Not in this case, look at here, in the three-membered ring, you are inserted in a circle, one of the carbon center is touches to the bottommost point where the vertical angle touches. That is taken as the least energy bonding molecular orbital. The remaining two carbons are touches the circle. These are the considered as doubly degenerated orbitals. Now this is about the non-bonding energy level. This is treated as anti-bonding molecular or anti-molecular orbitals. That is the reason he says that here. The other molecular orbitals are located wherever the carbons of the polygon touches the circle, and these molecular orbitals will be paired. These two are in the pair manner, right? Each carbon center on circle represents respective molecular orbital or representative molecular orbital. The molecular orbital, it means each carbon center touches to the circle that represents the molecular orbital. The molecular orbital present below the horizontal line is called as bonding molecular orbital. Suppose these two molecular orbitals are below the horizontal line are known as bonding molecular orbitals, or the molecular orbitals are above the non-bonding energy level, that is known as anti-bonding molecular orbitals. The molecular orbitals present on the horizontal line is called as present on the horizontal line. This is the horizontal line. Suppose these two orbitals are present on the horizontal line, that is known as non-bonding molecular orbitals. Now here the three types of molecular orbitals are there. The molecular orbitals below the non-bonding energy level, that is bonding molecular orbitals. The molecular orbitals above the non-bonding energy level, that is known as anti-bonding molecular orbitals. If the molecular orbitals are exactly coincident the line of horizontal line, that is known as non-bonding
molecular orbital.
molecular orbital or non-bonding molecular orbitals, right?
Yes, sir.
Later, after that, you can assign the electrons also. If the same, it is exactly what the Hooker is explained by taking the molecular orbitals. Here, the post-Muslim is taking a circle. He insert the polygon onto the circle in such a way that one of the carbon touches to the vertical line touches point, that is treated as the least energy bonding molecular orbital. The remaining carbon touches to the circle. Those circles positions are the remaining molecular orbitals position. If these molecular orbitals are below the non-bonding energy level, that is called as bonding molecular orbitals, or the molecular orbitals are above the non-bonding energy level, that is called as anti-bonding molecular orbitals, or the molecular orbitals are the same line on the non-bonding energy level, that is called as non-bonding molecular
orbitals.
Yes. Based on that, he assigned or he allotted the electrons by following the above Hookel rule. After filling the electrons, he estimated that or he observed that whether that system is having closed electronic configuration or not a closed electronic configuration. If it is showing closed electronic configuration, that is aromatic. If it is not showing any closed electronic configuration, that is anti-aromatic. That is the Prost-Muslim theory. Right, here I am going to show you the different molecules. This is the energy rising like that. For the particular first system, you take the cyclopropane. Sorry, cyclopropane. Just a minute. First system, cyclopropane. Why it is non-benzenide, I will tell you later. The cyclopropane systems, in a simple system, it is the property. Whenever it is a positive charge, cyclopropynium and you take a circle. This is the circle. First insert the this is the vertical line. This is the horizontal line. This is the horizontal line. Now insert the cyclopropylene system in such a way that one of the carbon to this point. Right. I'm inserting the cyclopropylene system like this. Right. One of the carbon touches to the vertical line and two carbons are touched to the above the non-bonding energy level. Now, this is the treated as one molecular orbital. This is treated as the two generated. Now it is shown like this. Right. Now we have how many electrons? Suppose you take the cyclopropylene cation first. Take the cation. How many only 2 5 electrons are 2 5 electrons are there. Now the 2 5 electrons are filled into this low energy molecular orbital. Or we can as a bonding molecular orbital. Only one bonding molecular orbital is the reason called orbital. The 2 electrons are into psi1. This is the psi2, psi3. These two are anti-bonding molecular orbitals. There is no electrons to fill in this. Now it is showing closed electronic configuration. Closed electronic configuration. This is suppose if you take right. If you take same non-bonding energy level, you take the anion, there is no change in the number of orbitals. Only 3 orbitals. One is the bonding molecular orbital. It is psi2 and psi3 are the anti-bonding. Now how many electrons are there in the system? Here the
four
electrons are there. The 4 electrons are there. The 2 electrons are in this. Remaining 2 electrons are mutually carried by the psi2 and psi3. Right. Now it is not now this is called as what do we call it as? Not a closed shell electronic configuration. That is known as non-aromatic. There is not just he used non-aromatic and aromatic. Non-aromatic. Right. This is about the cyclopropene ion. Right. Next, consider the cyclobutadiene.
Sir, if there is half-filled orbital, then we call it is not a closed electronic configuration.
Your voice is breaking, madam. Can you repeat again?
Sir, if there is
yes. Hello?
Hello, sir.
Yeah, tell me.
Sir, if there is a vacant orbital or half-filled orbital, then we call it is not a closed electronic configuration. Na?
When it is not a closed electronic configuration, it is non-aromatic. If it is having closed electronic configuration, it is aromatic.
Sir, ఇది అర్థం కాలేదు సార్. క్లోజ్డ్ ఎలక్ట్రాన్ కాన్ఫిగరేషన్ అంటే ఎలా చెప్తున్నారు అర్థం
Simple
కాలేదు.
అండి. It is very simple. There is a 3 metals are there. One psi1, psi2, psi3. Here the energy of the psi is a low energy, and right, psi2 and psi3 both are the same energy. Right. We have one are there 2 electrons according to the Abbo principle and Pauli's principle, Kuhl's rule. Lower energy orbital will be filled first. Later, higher energy. The electrons first filled into the psi1. It is low energy orbital. 2 electrons are filled in. There is no other electrons. These 2 are empty. Will not consider the orbitals. Only filled or half-filled electrons are considered. If the filled electrons are there, all the orbitals are filled orbitals. We are not considered the empty orbitals. Okay. The orbital which contains the electrons are filled or not, completely filled or not. If it is completely filled, that is known as closed electronic configuration. Or if it is half-filled, means only one electron is there in the orbital, that is called as not a closed electronic configuration, or unpaired electronic configuration. This is the paired electronic configuration, we called it as, or closed electronic configuration. And the second case is, suppose we have 4 electrons are there in the cyclopentadienyl cyclopropylium anion in the psi1, and 1 electron filled in I2 and 1 electron filled in C. Therefore, 4-5 electrons are filled like this. You consider here, these 2 electrons are filled. These 2 electrons are filled, not completely filled. Unpaired electrons. When unpaired electrons are there, that is called as unpaired electronic configuration, or not a closed electronic configuration. It is closed electronic configuration or unpaired electronic configuration. It is non-aromatic. Therefore, it is non-aromatic. It is aromatic. It is a filled electronic configuration, or paired electronic configuration, or closed electronic. The orbital is completely closed by filling the electrons. That is called as closed electronic configuration. Therefore, it is as aromatic.
Yes,
The
sir.
compound is aromatic. Understand?
Yes, sir.
Yeah. Okay. You can see the Proust-Muslin diagram in your book. You read it. If you have any doubt, you can ask me. And one more work. Up to the theory part is over in the aromaticity. The remaining unit, there is a compounds are there. Several aromatic compounds are given to you in your syllabus. That is the benzenide and non-benzenide. Just a minute, I will give you some work to you. Yeah. In the unit number 12, there is a non-benzenides of aromatic compounds are given. Those are 5-membered aromatic compounds, that is cyclopentadienyl anion, right? Ferrocene, 7-membered aromatic compound, tropylium salt are given. For those compounds, you need to prepare 3 preparations. That is the synthesis of that compound. 3 synthesis, 3 into 3, 9 reactions, right? And 9 properties. For each 3 properties, what you need to prepare, I will tell you later, but some of the important properties are also there. In the next class, I will discuss what you need to prepare, because these are all the reactions, and all are reactions. No need to explain much. You just understand the reaction by reading them, right? Wherever the concept is there, that concept, theoretical concept, I will explain. The remaining thing are only synthesis. Synthesis means that is the reaction and mechanism. If necessary, or if you have any doubt during the preparation of these reactions and understanding the mechanism, you can ask me. I will explain. Right? In the unit number 13 is also some some aromatic compounds are there. That is azulines and anthracenes and phenanthracenes, synthesis and properties. You need to read them. The minimum requirement is you need to prepare 3 preparations and 3 properties of each compound for exam purpose. Right? If you have any doubts during the preparation, ask me, I will clarify the doubts. But I only deal with the concepts, theoretical concepts. I will deal here. The remaining, if you manage to prepare, that will leave it to you. You to prepare well. Or if you have any doubts, I can clarify those doubts. Right?
So these questions are asked in long type question or in short type question?
Yeah, suppose write the postulates of Huckel theory and explain molecular orbital theory for the Huckel rule? That is the long answer question.
Sir, have you provided some notes?
This is the material whatever provided to you. That is the notes. Okay, that is the filtered material from the lots. So many number of well standard books. Okay, that is the consigned notes already.
Sir, have you sir YouTube class, YouTube links?
Yeah. Okay. Today I'm going to conclude the session. If you have any doubt, if you want, these running notes will be forwarded to you. Right? Any doubts? If you have, you can ask me.
Sir, the value means that is n is equals to odd or even. We can how can we calculate this one? Means
Look at here.
but
When you take the 4 and 5 from system, where is equal to number of electrons. Number where n is equal to the 0,
sir, can we
1, 2
calculate this
only.
by seeing
1,
the
2, 3.
diagram only?
Look at this. I'm finished. I'm going to finish
Yes,
it.
sir.
Later you will ask me. You take where n is equal to use these integer values. Whenever I am discussing the OT rule, where n is equal to odd or n is equal to even, number of carbons. Number of carbons. Okay.
Okay, sir.
Is it clear?
Yes, sir.
Right.
Thank you.
Is there any doubts?
Sir, in unit 1, we need to prepare also properties and chemical reactivity, or only for synthesis?
Yes.
Only for synthesis?
Synthesis and 3 synthesis, 3 properties.
Okay, sir. And what about the chemical reactivity?
That is property means chemical reactivity.
Okay, sir.
Right.
Okay, sir.
Hello.
Yeah, tell me.
Sir, assignments ఇచ్చారు కదా సార్ రాయమని చెప్పేసి.
This is not the place to discuss the assignments, right?
Okay, sir.
About the assignments, we are already discussing several times in the physical class. Those who are belongs to Vizag and Warangal and Tirupati, if you are there, any people? Yeah, if you are, most of them are from the 208 study center. For those people, I have already discussed this so many times. I have given so many tips for writing the assignment. It is the very already discussed topic. Don't ask me. You can ask your friends. Take the suggestion from your friends. That means from your classmates, and complete your assignments.
Okay, sir. Thank you.
Thank you. Okay.
Anyone from Odisha?
Yes.
Sir, anyone from Odisha? Students?
Yes,
I'm from Odisha. Sadanand Mishra.
Sir, name please.
Sadanand.
Sir, can I contact you?
In the chat.
ମୁଁ ସୁଚିସ୍ମିତା ଆଚାର୍ଯ୍ୟ ବୁଝିପାରୁଛନ୍ତି ତ?
ହଁ କୁହନ୍ତୁ।
ସାର୍ କଣ୍ଟାକ୍ଟ ନମ୍ବର ହେଲେ ଟିକେ ମାନେ କଥା ହୁଅନ୍ତେ।
ଚାଟ୍ ନାଁଟା କଣ?
ସେ ସଦାନନ୍ଦ।
ହଁ। ଆପଣଙ୍କ ନାଁଟା କଣ?
ସୁଚିସ୍ମିତା ପାଣିଗ୍ରାହୀ।
ଠିକ ଅଛି ମୁଁ ନମ୍ବରଟା ଦେଇଦଉଛି।
ସେଠି କଣ୍ଟାକ୍ଟ କଲେ ଆମେ ସେଠି ଜାଣନ୍ତେ ସେୟାର କରନ୍ତେ ମୁଁ ବି ଜାଣିପାରୁନି ଆକ୍ଚୁଆଲି।
ମେସେଜ କଲି ଆପଣଙ୍କୁ।
ଆଜ୍ଞା ସାର୍।